Okay, so full screen. I think we're up and running. So in the video, Geometry to Algebra to Calculus in 20 minutes, part 2, I happened to spot a little something that I thought was perhaps misleading in one of the drawings that I did. So I wanted to clarify it. As you probably understand, I'm at this stage, if you've been doing some of the lesson sets, that I'm a big fan of doing a lot of different types of problems 1 minute a day, 30 seconds, and maybe even getting some problems down to 5 seconds, as long as we keep getting touches on the ball. By that, I mean seeing it on a daily basis. Then over time, we can spread that out a little bit and just review every week or so, and then every couple of weeks. And then you can take this material into the next class. Because if you can't recall what we're doing, at some point you have to stop studying this discipline. All right, so here is a cubic, a perfect cube, volume equals side cubed, side times side times side. And I don't know how to depict this, but I started with a 2 by 2 by 2, and then we're going to increase it to a 2.001 by 2.001 to 2.001. And I happen to know what those are. I know that if I cube that, I get 2 equals 8, and 2.001 is equal to 8.012006001 without a calculator. Give me as many zeros as you want, and I'll give you that number. Give me 100 zeros. I don't care. I'll write what the product is because of the patterns that come from the cube, the geometric aspects of it. And so I talked about that in the second video on algebra to calculus, whatever. Right? But I said, let's change the dimension by 0.001. And that reminds me of a change in area. But we're changing volume over here. So what I wish I had said was that 0.001, and we'll use it from the knuckle to the top of my finger, is coming out from the wall. It's a very thin layer of thickness. So let me get my manipulative here. Okay. So here's your 2 by 2 by 2. And if I put, let's see if I can figure out how I'm, okay, yeah, there we go. So if we put a layer of volume on the box, well, what is that consisting of, that layer of volume? It's consisting of 3 squares, 1, 2, 3, right? With a little bit of thickness. Now, what's the little bit of thickness? It's that 0.001, and that's what I should have, tipped up. So I hope that talking about it is helping you to visualize what's going on. Because if you can visualize what's going on, then the symbolics we use to describe the process will make some sense. And what we do with René Descartes, thank you, René, helps us to study this without having to make the boxes. I can't tell you how many times I've made this box and lost it. Right? But if I kept adding layer of volume on this box, well, eventually I'm going to go from a box that is 2 by 2 by 2 to a box that's 3 by 3 by 3. And if I add up all of these layers from 2 to 3, then I'm going to get the net change in volume. I mean, I'm seeing it materialize right before my eyes. And now, how would I describe a square, a side length times a side length? Well, I hope you would say S squared. And how would you describe the number of squares that we put on the box to keep it a perfect cube? Well, I have a length times width. I hope this shows up, red marker. Let me get the other one just in case it doesn't. I have a length times width times height. It used to be 2 by 2 by 2, and now it's 2.001 times 2.001 times 2.001. And I've trapped a little increase in a function that's continuous from 2 to 2.001. I'm actually looking at how much the volume has changed. And if I change this from 2.001 to 2.002 to 2.002 to 2.002, I think I'm standardizing the thickness of the layers. Now, what happened if I did, instead of 2.001, let's go back here. What happens if this wasn't 2.001, but it was 2.000000001, then it becomes 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's the pattern you're going to get. And I think if I divide that by the change, 0.000000001, I hope I counted that right. I hope we can see that at that instant, at 2, this volume is going up at 12 units to 1. Right? And that's what we use for, the tangent line. The tangent line to 2, 8 would be slope of 12, 12 times x minus 2 plus 8. That would be the tangent. So we know a time of the day, a position, and a velocity. And that's where we're going to be going with this stuff initially at the calculus level. We'll talk about velocity, position, because it's the position, velocity, acceleration, because they're the easiest things to see. All right, so what does this become? It becomes, from a graphical standpoint, here's where René Descartes comes in to help. We can use 3s squared as representing the surface area of the cube, 3 sides, right? Because I'm only changing dimensions on length, width, and height. And if I do that, and I use 0.001 as my change from, say, 1.999 to 2, then I got a little bit of width, a little bit of change in x, all right? And this is usually going to be x, right? And so therefore, that's what we call dx. It's a concept, 0.01. And this is the height of the curve. And so each of these layers, one layer after another, is represented right here. You're looking at it. There's the 0.001. There's your 3 squares. Add an x value of 2. Then that height captures 12 units of change. The next one captures a little bit more. Right? What's the next one? The next one would be, I'd be at 0.001 thickness, but I would be squaring 2.001 because the box just got a little bigger, and the next level, the next layer is going to be a little bigger, and I'd keep doing that. And then I would be going up to 3 with all kinds of layering, thin layers of rectangular area with a little bit of thickness, and I have captured net change. Net changed, all right? From 2 to 3, I got the area times a little bit of thickness is giving me a representation of volume from 2 to 3. And that's what we do in calculus. We say, oh, I recognize where these changes are coming from. They're coming from studying the cubic from 2 to 3. And if I cube 3, 27, and I cube 2, 8, I get the net change in volume. And I look at the geometric process as to how it happens. Okay, it's awkward talking about this, right? Because it's not really depicted that often in the textbooks. I haven't seen one that depicts it, and yet that's what's going on. So I think it's really important you see this before you get to a calculus class. I really do think it's important to have some of these concepts in getting your head to start thinking about them now, because most students drop out of calculus. And what did I do? What was the study about? All right, and trying to make it more amenable to the learning process. Okay, so I felt like it was important to make that statement because, those layers were layers of volume, and in the depiction I gave you, it kind of hinted at area accumulation, and that's it. There is an area accumulation here. It's the surface area, right? But you got to give it a little bit of thickness to talk about the layers of volume that accumulate. All right. So whether you got that or not, don't care. You got to start the conversation, and you got to keep hearing it until you do get it. And then you're, I think, doing what's called learning. And that's my hope. Okay. All right. Stay safe and warm.